In geometry, we work with shapes a lot. A category of shapes that we work with is polygons. What is a polygon? A plane shape, plane just means two-dimensional, with a finite number of straight sides. And a polygon must be a closed shape, so we cannot have this opening right here. That's not a polygon. We have one of the sides, it's just extending randomly here. That's not a polygon. And then here we have a curve. Definitely not a polygon. A polygon is a two-dimensional shape with a finite number of straight sides. To review, equilateral means that all sides are congruent of equal measure. Equiangular means all angles are congruent of equal measure. And an interior angle is the angle between the adjacent sides of a straight-sided figure. So, for example, we have side 1, side 2, and the interior angle is the angle between. There's a word we use a lot. It's a type of polygon, and it's a regular polygon. A regular polygon is both equilateral and equiangular. And so that's very important to remember. A regular polygon is both equilateral, has all the same side lengths, and equiangular, all the same angle measures. Let's talk about the popular polygons, the ones that have specific names. So polygons are named based on the number of sides. A three-sided polygon is called a triangle. Four-sided is a quadrilateral. Five sides is a pentagon. Six sides is a hexagon. Seven sides is a heptagon, sometimes called a septagon. Octagon has 8 sides. A nonagon has 9 sides. A decagon has 10 sides. And a dodecagon has 12. Okay, if you notice, there's just an 11-sided polygon that doesn't have a name. It just doesn't occur as frequently, so it doesn't get a special name. Any other polygon with a different number of sides than the ones shown would be called number of sides gone, okay? Such as 11gon if you have 11 sides. If you have 13 sides, that would be a 13gon. If you have n number of sides, an unknown number of sides, that is called an n-gon. Start at one vertex of the polygon and draw in the diagonals for each. Complete the table below by counting the number of triangles inside each polygon and multiplying it by 180 degrees to find its interior angle sum. Okay, let's go back to a triangle. What do the interior angles of a triangle add up to? You may remember this neat little thing called triangle sum theorem. What do all three of these angles add up to? That's right, 180 degrees. Every triangle, its interior angles have a sum of 180 degrees. So I may not know the sum of all the interior angles of a quadrilateral as pictured here, but if I cut it up into triangles, now I have one triangle and two triangles. I have a triangle that has 180 degrees as its interior angle sum, because we know that. And then another triangle, which means I have another 180 degrees of interior angles inside this quadrilateral. Interesting. So we have a quadrilateral that is split into two triangles. The green triangle has an interior angle sum of 180 degrees. The yellow triangle has an interior angle sum of 180 degrees. And it's covering all four interior angles of our quadrilateral. So what is the interior angle sum of a quadrilateral? It would be 180 plus 180. A quadrilateral can be split into two triangles, and the sum of the interior angles of two triangles is 360 degrees. I've decided to start here. So this is a line from one vertex to one vertex, but that's a side, so that's not a diagonal. So we'll draw our other diagonal here, and then it needs to go to this is the starting vertex, so our next one needs to go here, and then our last diagonal, oh, that just completes the shape. So we have a five-sided polygon that's called a pentagon, and it looks like a pentagon can be made up of three triangles. Now, the interior angle sum of this green triangle is 180 degrees. The interior angle sum of the yellow is 180 degrees. And the interior angle sum of the blue is 180 degrees. Between these three triangles, we've covered all of the interior angles of this pentagon. And therefore, we can add up the 180s to get the interior angle sum of a pentagon, 180 times 3, which is 540. Here we have a six-sided polygon. That would be a hexagon. And that can be split into four triangles. Now I know that each triangle has an interior angle sum of 180, so if a hexagon has been split into four triangles, then the interior angle sum for a hexagon should be 180 times 4, and that is 720. Go ahead and continue drawing the rest of your triangles and filling in this table. All right, so once you've drawn all the diagonals to one vertex and you have filled in this table, is there some sort of a pattern? An n-gon, so a polygon with, we don't know how many sides, n number of sides, how many triangles does it have? A triangle literally has one triangle. Okay, a quadrilateral, a four-sided polygon, is made up of two triangles. A pentagon is made up of three triangles. A hexagon is made up of four triangles. A heptagon is made up of five triangles. Do we see a pattern here? Based on the number of sides, the number of triangles that will be made up by the interior angles of that polygon will be 2 less than the number of sides. So, how many triangles would an n-gon have? It would have n minus 2 triangles. So, that would be n minus 2. Okay, so then what is the sum of the interior angles of each of these polygons? Well, we took the number of triangles and we multiplied it by 180. 2 times 180 is 360. 3 times 180 is 540. 4 times 180 is 720. So to get the sum of the interior angles of a polygon that you don't know, like you don't yet know the number of sides, the formula for that, well, we would take the number of triangles, n minus 2, and we have to multiply it by 180. 180 degrees times the number of triangles inside of that polygon. Use the angle relationships in each of the diagrams below to solve for the given variables. Ooh, okay, now we're putting this formula to work. So, first of all, what kind of shape do I have? I want to know, classify it by its number of sides. So I have 1, 2, 3, 4, 5, 6 sides. All right, so what we have here is a hexagon. So the interior angles of a hexagon, they have a particular sum, and that sum is, we already have it. Look at this nice little table we've made for ourselves to help us out. Okay, so all the interior angles, these purple angles inside, all add up to 720 because that is the interior angle sum for a hexagon. All right, let's add up these angles. 121 degrees plus 96 degrees plus 101 plus 162 plus, ooh, what is this? It doesn't have a number, but we do know what that means. That means 90. And our last one is that variable x. This all adds up to be 720. We do have quite a few like terms that we can combine. Look at all these numbers. Let's add those up. Those add up to be 569 plus x equals 720. We'll subtract 569 from both sides to get x by itself, which makes x equal to 151. And these are angles, and our units are degrees. So x is 151 degrees. Okay, what about part B? What do we have here? We have a 1, 2, 3, 4, 5, 6, a six-sided polygon. But now it's telling me that every single interior angle is the same. Each interior angle is congruent. This is actually an equiangular hexagon. Oh, okay. So I'm going to do that same process where I add up all the angles inside. It goes 1x, 2x, 3x, 4x, 5x, and 6x. And that is equal to 720. Remember, that's the interior angle sum of a hexagon. So 6x is equal to 720, which means we're going to divide both sides by 6 in order to figure out what is x is 120. So each of these interior angles of this equiangular hexagon measure 120 degrees. Okay, what about a formula to find each interior angle of a regular polygon? Okay, a regular polygon is equiangular, just like this hexagon here. So, if all the angles are equal, I would like to take the sum of all the angles, which is 180 times n minus 2. And then, what did we end up doing? We ended up dividing that sum by the number of sides. We do have a variable representing number of sides, that is n. So, our formula to find each interior angle of a regular polygon, meaning all those angles are congruent, would be 180 times n minus 2 divided by the number of sides that polygon has. Very helpful formula that we'll be using. So let's talk about the other types of angles that a polygon has. We have the interior angle, but we also have the central angle, which is really important. And then you have your exterior angle, which is still relevant. So the central angle sum. I want us to think about this logically for a second. The central angle is kind of like the tip of each slice of pizza, if this were a big pizza. Okay? And so if I'm taking just the first bite, okay, I'm looking at that portion, what do all these angles add up to? Well, the angles add up to a full circle. Do you see a full circle right there? I see a full circle. How many degrees are in a full circle? So if someone does a 180, then they do a half turn. If someone does a 360, they do a full turn. That would be 360 degrees. Yes, so the central angles of any polygon, no matter the number of sides, always add up to 360 degrees. Okay, so I've drawn all the exterior angles. It looks kind of like a pinwheel or windmill or something's going on there. And as you go with your exterior angles, you do end up completing a full circle just like with your central angles. So although it's hard for me to show you visually, these angles, the exterior angles, always add up to be 360. So if we have a regular polygon, which is what they told us here, we have a regular polygon, so all the sides are the same length and all the angles are congruent. This is equiangular. So they want to know what is the measure of each central angle, this angle right here. Well, if the total central angles is 360 and we have a 5-sided polygon here, we would need to take 360 and divide it by 5. That gives us 72 degrees. So each central angle is 72 degrees. The exterior angles also add up to 360 degrees. We still have a 5-sided polygon, a pentagon, so each exterior angle would be the same, would be 360, the exterior angle sum, divided by however many exterior angles you have. And guess what? The number of exterior angles is the same as the number of sides. The number of central angles is the same as the number of sides. So whatever we do, we take 360 and we divide it by the number of sides. Here we have a hexagon, 1, 2, 3, 4, 5, 6-sided polygon. Okay, that would be one central angle. Each central angle is just the central angle sum divided by however many sides this polygon has, because that ends up being the slices of pizza, the number of sides. So this has 6, 360 divided by 6, that is 60. So each central angle measures 60 degrees on a regular hexagon, and each exterior angle also measures 60 degrees on a regular hexagon. The center of a round cut diamond is a regular octagon to optimize brilliance. Determine the measure of each interior angle of a regular octagon. Well, I do have a formula for each interior angle. So I just need to determine what n is. N is always the number of sides, and with an octagon, n is going to be equal to 8. So 180 times 8 minus 2 divided by 8. That would be 180 times 6 divided by 8. Put that in the calculator. And we get 135. This is the measure of an angle, so 135 degrees. All right, each interior angle of a regular octagon measures 135 degrees. What about the interior angles of other regular polygons? Find the sum of the interior angles of a regular nonagon and a regular 100gon. Well, we do have a formula for the sum of the interior angles, and it's n minus 2 times 180. So that's all we've got to do is plug in what is n. For a nonagon, what is n? A nonagon is a 9-sided polygon, so n is equal to 9 in this case. 9 minus 2 times 180. That is 7 times 180, which measures to be 1260. Okay, the sum of the interior angles of a nonagon is 1260 degrees. And for a 100gon, n is 100. So 100 minus 2 times 180 would be 98 times 180. That is 17,640. So the interior angle sum of a 100gon is 17,640 degrees. All right. Seems that once you have a lot more sides, you just get larger and larger interior angle sums. The interior angle of a polygon is 156 degrees. Name the polygon. Okay, this one's just a little bit trickier. We do have a formula for each interior angle. So we have each interior angle measures 180 times n minus 2, all divided by n. That's each interior angle. So if each interior angle equals 156, I have a big fraction is equal to a number. I can actually make this number into a fraction, and then maybe visually it'll be a little easier for you to see that you can cross multiply to solve this. So you have 180 times n minus 2 times 1. Okay, I know that doesn't change that. So that's equal to denominator times numerator, n times 156. So that's 156 times n. Okay, we can solve this equation. Distribute the 180. We've got to get rid of those parentheses so that we can get the ends together. Minus 180 times 2 is 360. Okay, I have an n term here and an n term there. I want them to be together. So I'm going to subtract 180n to get the ends onto the same side. Negative 360 is equal to negative 24n. Okay, so my last step will be to divide by negative 24 so that I can get n completely by itself. N is equal to negative 360 divided by negative 24, which is 15. The polygon that has each interior angle measuring 156 is the polygon with 15 sides. How do we call that? That is called a 15gon. So as a recap, fill in the formulas you've created in this lesson below. All right, and here are the formulas that we created during today's lesson. Remember, the interior angle is made up of the sides, but the central angle always comes from the center.